One bomb. 2,000 pounds of steel and explosive. Enough power to erase an entire building from existence. But the real secret wasn't what it destroyed. It was how it was built, layer by layer, to become the most devastating weapon of World War II. This is the inside story of the bomb that changed everything. A factory in Pennsylvania, 1943. The night shift is about to begin. Workers file into a massive warehouse where the temperature is kept exactly at 68 degrees Fahrenheit, not 1 degree higher, not 1 degree lower. On the factory floor sits a steel shell, 10 feet long, empty, waiting. By morning, that empty shell will be a weapon capable of obliterating a German U-boat pen buried under 20 feet of reinforced concrete. But right now, it's just hollow metal. What happens in the next 12 hours is one of the most dangerous, precise, and secretive manufacturing processes ever devised. Because building a 2,000-pound bomb isn't just about filling a case with explosives and hoping it works. It's about chemistry, physics, timing, and one wrong move means everyone in this factory dies. The foreman checks his clipboard. He's built 847 of these bombs. He's seen 3 men killed in accidents. He's watched entire shifts evacuated when a batch of explosive went unstable. He knows that what they're about to do is as close to controlled insanity as manufacturing gets. But there's a war on. The bombers need ordnance, and this factory will deliver no matter the cost. The process begins with the casing. The outer shell of the bomb isn't just any steel, it's a specific alloy, forged under intense heat and pressure, designed to withstand the shock of being dropped from 20,000 feet and the violent deceleration of impact. The steel has to be hard enough to penetrate concrete, but not so brittle that it shatters on contact. Finding that balance took 3 years of testing and cost the lives of dozens of test pilots whose bombs detonated prematurely or failed to explode at all. The casing arrives at the factory already shaped, a long cylindrical body with a tapered nose and a flat tail section. It weighs 400 pounds empty. The walls are 3 inches thick at the nose, tapering to 1 inch at the tail. Every inch of that steel has been X-rayed for flaws, stress-tested, and inspected by engineers who know that a single microscopic crack could cause the bomb to rupture mid-flight, killing the bomber crew instantly. But the casing is just the beginning. The real complexity lies in what goes inside. Layer 1, the base charge. Workers wearing thick rubber gloves and face shields approach the empty bomb casing lying horizontal on a wheeled cradle. They're carrying buckets of a substance that looks like wet sand but is actually amytol, a mixture of ammonium nitrate and TNT. This is the foundation, the first layer. It will account for roughly 60% of the bomb's total explosive power. But here's the thing about amytol: it's unstable. Temperature changes can cause it to crystallize. Moisture can cause chemical breakdown. Static electricity can detonate it. Which is why every worker in this room is wearing special shoes with non-conductive soles, why the air is kept at controlled humidity, why metal tools are forbidden, and everything, every bucket, every tool, every surface is made of wood or rubber. The first worker tilts his bucket and begins pouring the amytol into the bomb casing through the tail opening. The mixture flows like thick paste. Another worker uses a wooden paddle to spread it evenly against the inner walls of the casing, working carefully to eliminate air pockets. Air pockets are death. When the bomb detonates, any trapped air creates an uneven pressure wave that can cause the casing to fragment unpredictably, reducing the bomb's effectiveness or causing it to fail entirely. The process takes 2 hours. Pour, spread, compress, pour again. The amytol builds up in layers, each one packed tightly against the last, until the entire interior of the bomb casing is lined with explosive material 4 inches thick. But they're not done, not even close, because pure amytol, while powerful, isn't powerful enough. The Germans have developed concrete bunkers so thick that conventional explosives just chip the surface. Allied bombers need something with more punch, something that doesn't just explode, it detonates. And that's where Layer 2 comes in, the booster charge. If you're fascinated by hidden WW2 secrets like this, make sure to like the video, because what comes next is the most dangerous part of the entire process. A supervisor wheels in a cart carrying small metal cylinders, each one sealed and labeled with red warning tags. Inside those cylinders is RDX, Research Department Explosive, one of the most powerful non-nuclear ever created. RDX is roughly 1.5 times more powerful than TNT, but it's also incredibly sensitive. A sharp impact can set it off. A spark can set it off. On a hot day, if the temperature rises above 80 degrees, RDX can become so unstable that it detonates spontaneously. Which is why this factory maintains that precise 68-degree temperature, why the RDX is stored in a separate building half a mile away, and why only 2 workers are allowed to handle it at any given time, and why everyone else clears the floor when the RDX arrives. The first worker opens one of the cylinders. Inside is a pale yellow powder that looks almost harmless. He carefully scoops a measured amount into a metal bowl. Metal is allowed here because the RDX is mixed with wax that reduces its sensitivity, and begins kneading it like dough. The wax binds the RDX particles together, making it safer to handle while preserving its explosive power. He shapes it into a thick disc, roughly the size of a dinner plate. This disc will sit at the center of the bomb, surrounded by the ammitol. When the bomb's fuse triggers, it will ignite the RDX first. The RDX will detonate with such force and speed that it creates a shock wave traveling at 27,000 feet per second, faster than any bullet ever fired. That shock wave will compress the surrounding ammitol to the point of detonation, creating a secondary explosion that's exponentially more powerful than either explosive alone. It's called a shaped charge effect, and it's the secret that makes the 2,000-pound bomb capable of penetrating bunkers that would laugh off a conventional explosive. The worker lowers the RDX disc into the bomb casing, positioning it carefully at the exact center. Alignment is critical. If the booster charge is even slightly off-center, the detonation wave will be asymmetrical, and the bomb will lose half its penetrating power. He uses a plumb line and a wooden jig to check the position 3 times before he's satisfied. Then he steps back. The RDX is in place, Layer 2 complete. Now comes Layer 3, and this is where it gets truly strange. The fuse assembly. Most people think a bomb is simple. Light the fuse, it explodes. But a bomb dropped from 4 miles up, traveling at 300 miles per hour doesn't work that way. It needs to know when to explode. Too early, and it detonates in the air, wasting its energy. Too late, and it buries itself so deep in the ground that the explosion is contained, again wasting its potential. The bomb needs to explode at the exact moment of maximum effectiveness. And that means it needs to think. Enter the fuse, a mechanical marvel of gears, springs, and detonators so precise that Swiss watchmakers were recruited to design them. The fuse assembly is installed in the nose of the bomb, threaded into a cylindrical cavity that leads directly to the RDX booster charge. It's about the size of a soda can and weighs 3 pounds. Inside are dozens of components, each one machined to tolerances measured in thousandths of an inch. There's a small propeller on the front that spins as the bomb falls, using air resistance to arm the detonator. There's a barometric sensor that measures air pressure to determine altitude. There's an impact sensor, a spring-loaded pin that gets compressed when the bomb hits the target. And there's a delay mechanism, a clockwork timer that can be set before the mission to make the bomb explode instantly on impact, or 1/10 of a second after impact, or even several seconds after impact, depending on the target. But here's the truly ingenious part. The fuse doesn't arm until the bomb has fallen at least 500 feet. This is a safety feature to protect the bomber crew. If a bomb accidentally releases while the plane is still on the runway or at low altitude, the fuse stays inert. The bomb just thuds into the ground like a very expensive paperweight. Only after the propeller has spun enough revolutions to indicate a proper drop does the internal mechanism unlock, allowing the impact sensor to trigger the detonator. A technician carefully threads the fuse into the nose of the bomb, turning it slowly, feeling for the threads to catch. One wrong move, one cross-threaded connection, and the bomb is useless. Or worse, it becomes live immediately, turning the factory floor into a crater. He tightens it with a special wrench, then double-checks the safety pin that keeps the propeller from spinning. The pin is painted bright red. It will be pulled out by the ground crew just before the bomb is loaded onto the aircraft. Until then, the bomb is theoretically safe. Theoretically. Workers have died when safety pins failed, when fuses malfunctioned, when bombs that were supposed to be inert suddenly weren't. The technician steps back, wipes sweat from his forehead despite the cool air, and marks the bomb with a chalk symbol indicating the fuse is installed and functional. Layer 3, complete. But the bomb still isn't finished. There's one more layer, one more component that determines whether this weapon will work as intended or become a dud that enemy engineers recover and study, learning Allied secrets and developing countermeasures. Layer 4, the arming wire. And if you want to discover more untold WW2 stories and deadly hidden technologies, subscribe now, because what you're about to see next will blow your mind. The arming wire is deceptively simple, a thin metal cable, about the thickness of a guitar string, that connects the fuse to a shackle on the bomb rack inside the aircraft. When the bomb is released, the wire pulls free, removing the final safety and allowing the fuse to fully arm during descent. But the wire has to be exactly the right strength. Too weak, and it breaks prematurely from vibration or wind buffeting, arming the bomb while it's still attached to the aircraft. Too strong, and it doesn't release cleanly, either keeping the bomb stuck to the aircraft or damaging the fuse mechanism on release. Engineers spent months testing different wire gauges, different materials, different attachment points. Pilots reported bombs that released but didn't arm, bombs that armed but didn't release, bombs that fell off accidentally during turbulence and detonated in midair directly beneath the aircraft, destroying the plane and killing everyone aboard. The final design uses a braided steel wire, with a tensile strength calculated to break at exactly 200 pounds of force, enough to withstand any normal flight conditions, but guaranteed to snap when the bomb's weight pulls against it during release. A worker threads the wire through an eyelet on the fuse, twists it into a secure loop, and attaches the other end to a small metal ring that will hook onto the bomb's shackle. He tugs on it gently, testing. It holds. He tags it with another chalk mark. The bomb is now fully assembled. Casing, Amatol base charge, RDX booster, precision fuse, arming wire. 4 layers, 2,000 pounds. Enough explosive force to create a crater 40 feet wide and 20 feet deep. Enough power to generate a pressure wave that will rupture internal organs 200 feet away, even if you aren't hit by shrapnel. Enough destruction to collapse a 5-story building into its own basement. But it's still not ready to leave the factory, because a bomb is only as good as its paint job. This sounds absurd. Paint on a weapon designed to explode? But the paint serves 3 critical purposes. First, identification. Bombs are painted different colors to indicate their fuse type and explosive fill. A gray band means standard Amatol. A yellow band means high explosive with RDX booster. A green band means chemical weapon. A red band means incendiary. Ground crews loading bombs in the dark, often under enemy fire, need to identify the right ordnance instantly. The wrong bomb on the wrong mission means failure, or worse, friendly casualties. Second, rust prevention. These bombs might sit in a damp aircraft hangar for weeks before they're used. Exposed steel rusts. Rusted steel weakens. Weakened steel means the casing might rupture on impact before the explosive detonates, again causing a dud. A thick coat of rust-resistant paint solves this. Third, and most surprisingly, Aerodynamics. The paint smooths microscopic imperfections in the steel surface, reducing air resistance and making the bomb fall more predictably. In testing, unpainted bombs showed a deviation of up to 100 feet from their aim point compared to painted bombs dropped under identical conditions. Workers roll the completed bomb to the paint booth, a sealed room with massive ventilation fans that pull toxic fumes away from the breathing zone. They hang the bomb from chains and spray it with compressed air gun, covering every inch in thick olive drab paint, then add the identification bands, in this case gray and yellow, indicating a standard high-explosive bomb with booster charge. The paint dries in 30 minutes under heat lamps. And finally, the bomb is complete. From empty shell to finished weapon in 12 hours. But there's one final test. The drop test. Before any batch of bombs leaves the factory, one is selected at random and subjected to what workers call the lottery. The selected bomb is taken to a testing range 5 miles from the factory. It's loaded into a crane and lifted to a height of 50 feet. Then it's released. It falls. It hits a concrete pad designed to simulate the hardest possible impact. And one of 3 things happens. Best case, the bomb doesn't explode because it's not fused, but the casing remains intact, proving the structural integrity is sound. Middle case, the casing cracks or deforms, indicating a manufacturing flaw, and the entire batch is rejected and melted down for scrap. Worst case, something in the manufacturing process went wrong. The explosive is unstable and the bomb detonates on impact without a fuse. The explosion kills the test crew, destroys the equipment, sets the factory back days. But it saves the lives of the air crew who would have loaded that bomb into their aircraft, flown it over enemy territory, and had it detonate in their bomb bay at 20,000 feet. Today's test goes well. The bomb hits the pad with a thunderous clang. The casing dents but doesn't rupture. The explosive remains inert. The batch is approved. By dawn, 120 bombs from this night's production are loaded onto trucks and driven to a nearby airfield where B-17 flying fortresses are being prepared for a mission over occupied France. But what exactly makes this bomb deadlier than earlier designs? Why did Allied engineers spend so much effort perfecting every layer, every component, every microscopic detail? The answer lies in a catastrophic failure that occurred in 1942 over Germany, a failure that killed hundreds of airmen and forced a complete redesign of Allied bombing strategy. August 17, 1942. The first major American daylight bombing raid on Europe. Target: the rail yards at Rouen, France. 96 B-17 bombers, each carrying 12 500-pound bombs. The raid is supposed to cripple German logistics in the region. The bombers fly in tight formation, the way they've trained. They reach the target. Bombardiers peer through their Norden sights, calculating wind speed, altitude, target velocity. Bomb bay doors open. The order comes through the intercom. Bombs away! And the bombardiers press their release triggers. Hundreds of bombs tumble from the aircraft, stabilizing fins catching the air, fuses arming as they fall. They should have devastated the rail yards. Instead, 40% of them are duds. They hit the ground and don't explode. They just bury themselves in the dirt, inert, useless, wasting the mission, wasting the fuel, wasting the risk. German engineers recover dozens of unexploded American bombs, transport them to laboratories, carefully disassemble them, and discover the fatal flaw. The explosive filling has cracked. The bombs were manufactured too quickly. The amytal wasn't packed densely enough. Air pockets formed. During the violent deceleration of impact, the explosive charge shifted inside the casing, breaking apart and preventing proper detonation. The Germans are delighted. American bombs are junk. They start ignoring many of the unexploded ones, letting them sit in the rail yards, knowing they pose no real threat. Allied command is furious. Hundreds of airmen risked their lives for nothing. The entire bombing campaign is in jeopardy. An emergency order goes out to every bomb factory in America. Fix this. Find out what's wrong and fix it now. Engineers tear apart the manufacturing process. They analyze every step. They test different explosive formulations, different packing methods, different casing designs, and they discover the problem: speed. The factories are pushing production so hard, trying to meet impossible quotas, that quality control has collapsed. Bombs are being assembled in 8 hours instead of 12. Explosive is being poured too quickly, without proper compression. Fuses are being installed without adequate testing. The solution is painful but necessary. Slow down. Do it right. Even if it means producing fewer bombs, produce better bombs. New protocols are implemented. Every batch of explosive must be tested for density and consistency. Every bomb casing must undergo ultrasonic inspection for cracks. Every fuse must be tested 3 times before installation. The loading process is redesigned to eliminate air pockets. Instead of pouring Amitol in loose, workers now use hydraulic presses to compress it in layers, ensuring complete density throughout. The changes slow production by 30%. Factories that were producing 200 bombs per day now produce 140, but the dud rate drops from 40% to less than 2%. By mid-1943, American bombs are the most reliable in the world. More reliable than British bombs, more reliable than German bombs, more reliable even than the pre-war designs, because the quality control forced by the 1942 failures has created a manufacturing process that's essentially flawless. And this brings us back to that factory in Pennsylvania, to that single 2,000-pound bomb rolling out the door at dawn, loaded onto a truck, driven to the airfield. This bomb represents everything learned from those early failures. Every layer is perfect. Every component is tested. The casing is inspected by X-ray. The explosive is compressed to exact specifications. The fuse is calibrated by technicians who've assembled thousands. The paint is applied with precision. This bomb will work. It will fall from 22,000 feet, traveling at terminal velocity. The fuse will arm. The bomb will penetrate 15 feet of earth and 8 feet of reinforced concrete. And then it will detonate with a force equivalent to 1,200 pounds of TNT, creating a shock wave that travels outward at supersonic speed, pulverizing everything within a 50-foot radius, causing structural failure in buildings 200 feet away, shattering windows half a mile distant. But how does it actually work in combat? What happens when one of these bombs is loaded onto a B-17, flown 800 miles into hostile territory, and dropped on a target swarming with anti-aircraft fire? March 6, 1944. An airfield in England. Ground crews are loading bombs onto a B-17 named Memphis Belle. Today's target is a ball bearing factory in Schweinfurt, Germany. Ball bearings are critical to German war production. They're used in tanks, aircraft, U-boats, every piece of machinery that keeps the Nazi war machine running. Destroy the factory and you cripple German industry for months. The ground crew uses a hydraulic lift to raise a 2,000-pound bomb toward the bomb bay. The bomb is painted olive drab with yellow and gray bands. It has a chalked number on the side, 3847. That's the production batch. If this bomb fails, investigators will track down every other bomb from batch 3847 and test them all. The crew carefully positions the bomb onto the shackle, a mechanical release clamp inside the bomb bay. The shackle closes around the suspension lugs welded to the bomb casing. A crew chief attaches the arming wire, threading it through the eyelet and hooking it to the shackle. He tugs gently. It holds. He gives a thumbs up. The bombardier, a 22-year-old lieutenant from Ohio, climbs into the nose of the aircraft and visually inspects the bomb load. 4 2,000-pounders, 8,000 pounds of explosive power, enough to level half a city block. He checks that the safety pins are still installed in the fuses, painted red so they're visible even in the dark. Those pins will be pulled by the ground crew just before takeoff. Until then, the bombs are safe. In theory. The engines roar to life. The B-17 taxis to the runway. Ground crew members run alongside, pulling the safety pins as the aircraft rolls past. The pins dangle from red streamers, collected and counted to ensure every bomb is now live. The plane accelerates, lifts off, climbs, joins a formation of 300 other bombers, all heading east toward Germany. The flight takes 3 hours. At 22,000 feet, the temperature inside the unpressurized aircraft is minus 40 degrees. The crew wears heated suits, but it's not enough. Ice forms on every surface. The bombardier's breath freezes on his oxygen mask. His fingers are numb even through insulated gloves, but he has a job to do. 30 miles from the target, the formation encounters flak, German anti-aircraft fire. Black puffs of explosive appear in the sky around them. Shrapnel rattles against the aircraft's aluminum skin. A bomber to their left takes a direct hit. Its wing tears off. It spirals down, trailing fire. No parachutes. The bombardier forces himself to focus. He peers through his Norden bomb sight, a complex optical computer that calculates the exact moment to release the bombs based on altitude, airspeed, wind velocity, and target distance. He inputs the data. The crosshairs settle on the target, the factory complex, visible as a cluster of rectangular buildings surrounded by rail lines. More flak. The aircraft shudders. Alarms sound. They've been hit. Engine number 3 is losing oil pressure. But they're on the bomb run now. No evasive maneuvers. Straight and level flight. The bombardier's finger hovers over the release trigger. The Norden site's computer ticks through its calculations. And then a tone sounds in his headset. Release point. He presses the trigger. Mechanical clamps release. The shackles open. 4 bombs drop free. The arming wires pull taut. Snap. The bombs tumble into the slipstream. The propellers on their noses begin spinning. Inside each fuse, a mechanism unlocks. The bombs are now live. They fall. The bombardier watches them through the sight. 4 dark shapes, getting smaller. They stabilize, fins correcting their tumble. They fall faster now, accelerating past 500 miles per hour. At 1,000 feet above the target, the barometric sensors register the pressure change. Internal safeties release. The impact triggers arm. First bomb hits. It punches through the factory roof, through 2 floors of machinery and workspace, into the ground floor, through the concrete foundation, and 8 feet into the earth below. 1/10 of a second after impact, the fuse triggers. The detonator fires. A small explosion ignites the RDX booster charge. The RDX detonates at 27,000 feet per second. The shock wave compresses the surrounding amitol beyond its detonation threshold. The amitol explodes. The steel casing, compressed beyond its structural limit, fragments into thousands of pieces traveling at supersonic speed. The explosion vents upward, following the path of least resistance, back up through the hole the bomb made on entry. The ground floor erupts. The pressure wave expands outward, tearing through walls, collapsing support columns, igniting fuel stores and chemical supplies. The second and third bombs hit within 2 seconds, compounding the destruction. The factory roof collapses. Machinery weighing tons is thrown through the air like toys. Workers who survived the first explosion are killed by the second or third. Fires ignite across the complex. Secondary explosions tear through adjacent buildings as stored materials cook off. By the time the 4th bomb detonates, there's nothing left but rubble and fire. The Memphis Belle banks away, trailing smoke from its damaged engine, but still flying. The bombardier looks back at the target. The factory is gone. Completely gone. Just a crater and flames. But here's what most people don't know about that mission. 60% of the bombs dropped that day were duds. Not from Memphis Belle. Her bombs worked perfectly. But across the entire formation of 300 bombers, carrying over 1,000 bombs total, more than 600 failed to detonate. Some had defective fuses. Some had cracks in the explosive filling that occurred during loading or flight. Some hit the ground at odd angles that prevented the impact triggers from firing. The raid is considered a success because enough bombs worked to destroy the target, but the dud rate is still unacceptable. More refinements are needed. And this is the nature of weapons engineering during wartime. It's never finished. Every mission reveals new failure modes. Every failure demands new solutions. By late 1944, American bombs have undergone 37 separate design revisions. The fuses are more reliable. The explosives are more stable. The casings are stronger. The dud rate drops to 5%, then 3%, then 1%. By the end of the war, American bombs are so reliable that bombardiers trust them completely. They know that when they press the release trigger, the bomb will fall, it will arm, it will detonate, and it will destroy the target. That trust is built on the bodies of thousands of workers who died in factory accidents, on the failures of early missions, on the engineers who spent years perfecting every layer, every component, every microscopic detail. And the 2,000-pound bomb becomes the standard. Not because it's the biggest. The British developed bombs weighing 12,000 pounds, designed to create earthquake effects that collapse underground bunkers. Not because it's the most powerful. Shaped charges and incendiary weapons produce more localized destruction. But because it's reliable. Because it works. Because a bomber crew loading these weapons knows that they're carrying ordnance that will do its job, every time, no matter what. By 1945, American factories are producing 50,000 bombs per day. That's over 18 million bombs per year. Each one built the same way. Each one inspected to the same standards. Each one a masterpiece of engineering and manufacturing precision designed for a single purpose: to fall from the sky and explode with maximum effect. But the story doesn't end in 1945. When the war ends, the bombs don't disappear. Millions of them are stored in depots around the world, sold to allied nations, reused in later conflicts. And some are never used at all. They sit in bunkers and warehouses, slowly aging, the explosives inside degrading, becoming more unstable with each passing year. Even today, construction crews in Europe regularly uncover unexploded bombs from World War II. London, Berlin, Paris. Cities that were bombed 80 years ago still have ordnance buried beneath their streets. When a bomb is found, the area is evacuated. Bomb disposal teams carefully excavate around it. They X-ray the casing to check for cracks. They inspect the fuse to determine if it's still active. And then they face a choice: defuse it or detonate it. Defusing means carefully removing the fuse, which after 80 years might be corroded, unstable, or booby-trapped. One wrong move and the bomb explodes, killing the disposal team and everyone nearby. Detonation means controlled destruction, packing explosives around the bomb and blowing it up intentionally, accepting the damage to nearby buildings and infrastructure as preferable to the risk of accidental detonation. Most of the time, they detonate. It's safer. Which means that even now, 80 years after the war ended, the 2,000-pound bombs built in that Pennsylvania factory are still exploding, still destroying, still fulfilling their original purpose. And there's a strange poetry to that. These weapons were built to last. They were engineered with such precision, such care, such attention to every layer and component that they remain functional decades after their creators died. The workers who poured the amatol, who installed the fuses, who painted the casings, they're gone. The engineers who designed the bombs, who calculated the precise mixture of explosives and the optimal fuse timing, they're gone. The pilots who dropped them, the bombardiers who aimed them, the crews who loaded them, almost all gone. But the bombs remain, sleeping in the earth, waiting, and occasionally they wake up. Berlin. A construction crew is excavating a foundation for a new apartment building. The shovel of an excavator hits something metallic. The operator stops, climbs down, inspects. It's a bomb. Olive drab paint, faded but still visible. Yellow and gray bands. A chalked number, barely legible after 80 years underground, batch 3847. The same batch loaded onto the Memphis Belle in 1944. Police cordon off 6 city blocks. Bomb disposal experts arrive. They carefully uncover the bomb, clearing away dirt with hand tools, terrified that the slightest vibration might trigger the impact fuse. They examine the fuse assembly. It's corroded but still mechanically sound. The safety mechanisms that were supposed to make it inert after a few years have failed. The bomb is still live. They can't defuse it. The risk is too high. They pack the area around the bomb with sandbags, then place a smaller explosive charge next to the fuse. Everyone retreats to a safe distance. The charge detonates, destroying the fuse assembly. And the bomb, designed to level a factory, finally fulfills a different purpose. It's rendered safe, neutralized. After 8 decades, its war is over. But there are thousands more still buried. In London, in Hamburg, in Tokyo, in cities that have built entire modern districts on top of battlefields, where every excavation is a potential encounter with death from another era. Engineers estimate it will take another 100 years to find and clear all the unexploded ordnance from World War II. Which means that the 2,000-pound bombs built layer by layer in Pennsylvania factories, designed to last one mission, will still be claiming lives in the 22nd century. That's the legacy of perfect engineering applied to weapons. You build something so well, so precisely, that it outlasts its purpose, outlasts its creators, outlasts the war itself. The bomb endures. And in that endurance is a warning, because we've gotten even better at building weapons since World War II. Modern bombs are more precise, more powerful, more reliable. They use computers instead of mechanical fuses, GPS instead of bomb sights, explosives that make RDX look like fireworks. But they're built with the same philosophy. Every layer matters, every component is tested. Every detail is perfected. Because in war, second best means dead. And so we engineer death with the same care that we engineer anything else, layering precision on top of precision, building weapons that will work perfectly when called upon to destroy. The 2,000-pound bomb that leveled that factory in 1944 wasn't evil, it was just steel and explosive. Assembled by workers who went home to their families each night, designed by engineers who were solving a problem, used by pilots who believed they were fighting for freedom. But evil or not, it killed thousands. And it continues to kill decades later because it was built too well to die. That's the real secret inside the bomb. Not the RDX booster or the precision fuse or the carefully compressed amatol. The secret is that we built it to last. And it did. If you love discovering the deadly secrets of WW2 weapons, make sure to subscribe. A new video revealing even more hidden truths is coming very soon. Because the history they don't teach you in school is the history written in steel and explosive, in the weapons we build and the lives they take. And that's a history that never truly ends. It just waits in the ground, patient and deadly, for someone to dig too deep.